something like this. So the objective of this exercise is that we are going to understand how a black hole table is used in a reservoir simulator or any other simulation package where actually a black hole table is required as an input. And just as a thought kind of experiment to exemplify some of the issues and some of the importance of the different topics that both Singh and Curtis have mentioned, we're going to pretend that we are actually one grid cell in a reservoir simulator, and we'll try to find the associated black hole table properties based on the two fundamental inputs, which is GOR and pressure. And we then hopefully are going to learn how a program thinks when it comes to a BOT. So that's kind of the basis of this exercise. The starting point, which is very, very important, and it's a plot provided in this black hole table Excel file that everybody has gotten. It's an extrapolated black hole table, continues at the critical point as we see right here. Here we see the GOR, so the solution GOR, and the inverse of solution CGR, and the units is scuffs per barrel. And for all of you who haven't seen a curve like this before, it's important to emphasize that everything inside of this blue region is the so-called two-phase region. So this is, as we discussed earlier, just a slice through the PT diagram. So just another way of I guess, analyzing the pressure composition space or pressure GOR space. And outside of this, if we're above this red line, we are essentially in a single-phase gas region. And if we are below this green line, we're in the single-phase oil region. Important to emphasize again, I think looking at the numbers, most of you have been able to downloading this black hole PBT table. But if you haven't, just feel free to send us an email to info@whitson.com and we'll provide it. It will probably be a little bit too late to actually do the exercise, but some of these things we'll just do together, so you'll be able to learn from that as well. The first exercise is fairly, I guess, straightforward, at least 1A, and we'll consider three different cases right here related to the black hole table that you all should have downloaded, and we'll take a look at that black hole table just in a minute. Or actually, I think we'll just look at it real quick right now. So I think everybody should be able to see the screen right in front of us. Maybe that was a little bit difficult. Let's see here. So in this black hole table that is provided in Excel format, we have 4 different sheets that is not hidden, and that's the saturated part of the PBT table. This is just in tabulated format. We have the saturated and undersaturated part of the table that we'll get back to, and we have this advanced plot that we'll use graphically in the first part of the exercise. And then we have a last sheet that we'll just use for an example, just to calculate the oil and gas saturations in that grid cell, which we will find to be two-phase saturated. So hopefully you all are a little bit familiar with these 4 sheets. Nothing more than that as of right now. The 3 different cases that we will consider is a case where we, in this imaginary grid cell, we have a gas to oil ratio of 1504 scuffs per barrel, and the pressure in this particular cell in the first case is 8,500 psi. In the second case, the GOR is around 15,000 scuffs per barrel, and the grid cell pressure is again 8,500 psi. And then we have a GOR case, which is 10,000 scuffs per barrel, and a grid cell pressure of 5,000 psi. And in the first part of the exercise, you should use to plot the GOR versus pressure plot and determine what type of fluid is associated with each of the cases above. Is it two-phase saturated? Is it a single-phase oil? or is it a single phase gas? The second question is, what are the associated black oil PVT properties, so the volume factor that Curtis talked about and the viscosities for each of these different cases? That's number B. And what I was thinking that we could do is just to step through the first part of the exercise together graphically. And everybody should have this this table in front of you, I hope. And we agreed that the first case is a GOR of 1500. So that's the first information we need to plot into this plot. That's the information that our simulator grid cell have been given, together with the pressure of 8,500 psi. We see that the area where these two lines intersect is outside of the two-phase region, which means and draws the following two observations. We're outside the two-phase region, hence we are a single-phase fluid, and since we are below the green line, this is a single-phase oil. So we've already solved the first part of this exercise. Similarly, for the second case, we're dealing with a GOR of close to 15,000 scuffs per barrel. The reservoir pressure is yet again the same, and we see yet again that we have an intersection outside of the two-phase region, which leads to the conclusion that we're still single phase, and since we're above the red line, we are a single phase gas at initial conditions. And we'll find these, or not the initial conditions, but at these conditions. The last case is a very interesting case. It's a case where the GOR is 10,000 scuffs per barrel, and the reservoir pressure is 5,000 psia. And as we're seeing right now, this intersection is within the two-phase region, and we can conclude that we have a case that is two-phase saturated. Very good. For the second part of the exercise, what we'll have to do is to jump into the Excel sheet to answer what are the associated PVT properties to case A, case B, and case C. So case 1 there, we had a GOR that was provided to this grid cell of 1500. So what we have to always start with is this saturated data table right here. And we see that our solution GOR is given in this particular column right here. And it is increasing all the way up to, and it's not a coincidence that we picked 15,004. That's because it is given here, so we don't have to interpolate any data points. But we see that at these conditions right here, the saturation pressure of the fluid with this associated GOR is 5,800. We see that this is below the pressure that was given in the grid cell, which was 8,500. So we know that we're at the undersaturated conditions. So when that's the case, we have to go into the saturated table, which is the second sheet. Undersaturated table, sorry. That's the second sheet. We need to find the saturation pressure of 5,800. And we need to also go to the pressure that's given here. There I've cheated a little bit just to highlight that for you. And we find that the PVT properties that is relevant at those conditions when we're dealing with a single phase oil is a formation volume factor of 1.63. The solution GOR is equal to the GOR given, and we have a viscosity of around 0.8 or 0.9 essentially centipoise. So that was the first part of that exercise. The second exercise was when the GOR was around 15,000 scuffs per barrel. What we see here, if we just follow the solution GOR column given in column C, is that the critical point ends at 5,724 scuffs per barrel. So we actually need to start to investigate the inverse of solution GOR. And we find at some point down here that 15,024 is given at giving us a saturation pressure of 7,100. This is below 8,500, so we see yet again, just not graphically as we did earlier, that we're at the undersaturated condition. So we need to yet again move into the undersaturated table, find 7,100, which was the saturation pressure given, go from the saturation pressure and up to 8,500, and then find the gas relevant properties, which is given by the BGD, the RS, and the viscosity right here. Maybe give the viscosity one more digit right here. And these are also properties that we'll use in the last exercise. The last case that we were given was the case where the total GOR was 10,000.
No.
Yeah. So the total GOR was 10,000, and the pressure was 5,000. In this particular case, we see that the GOR is 10,000 right here, but that corresponds to a saturation pressure of 8,500, which is actually above the pressure that we've been given. So we know that we are at saturated conditions in situ. So then we simply need to find the properties associated with 5,000 in this table right here. That means that we have actually a oil saturation and a gas saturation in the reservoir. So here we have an oil at 5,000 psi with 1.58 in formation volume factor and a solution GOR of around 1,200. And similarly on the gas side we have a BGD and a RS of 36 barrels per million. And actually, this information, just for example purposes, can be used to calculate the saturation of the gas and oil phase at those conditions. So if we just simply copy paste these values right here in blue into the calculate saturation pane or sheet, I guess. And then we do that also for the gas, also, oh, that was viscosity, and we also do that for the gas side. And we include that the total GOR was 10,000. These properties right here to the right should already be I guess programmed for you, so the formulas are there and the equations are given in this slide that's just pasted in here. And we see that most of the saturation or most of the gas in this grid cell, this imaginary grid cell, or most of the volume is occupied, or saturation is occupied by gas, so 86%, and the rest is then an oil saturation of around 14%. Very good. So that was the first exercise, and this is going fairly quickly. Just to summarize, these are the properties that or results from that exercise is given right here for case 1, 2, and 3. Number 3 has properties for both phases. And we'll bring this into the second exercise, which is a little bit more simple, I think, for or maybe people are more used to it. And the first part of the exercise is that we're going to assume that the single phase oil case, so the case I, the first case, has PVT properties representative of one entire reservoir, where the hydrocarbon pore volume is 100 million reservoir barrels. And our job is to calculate the original oil in place. And the follow-up question to that is we have a single phase gas case, which was the case number 2 that we just went through. and that has PVT properties representative of an entire reservoir. Again, the hydrocarbon pore volume of this field is 100 million reservoir barrels. What is the oil in place? Very good. So we'll walk through this one slowly. This exercise A. So for the single phase oil case, the oil in place formula is simply given by hydrocarbon pore volume divided by BOI. We have been given the BOI to be, we found that in the table to be 1.63, and our final answer is 61.35 million barrels. Stock tank barrels. The second case for the oil is, no, for the gas, sorry, the single phase gas. What is the original oil in place? And here we'll simply just show you all two different ways of solving this exercise, where the first alternative is that we first calculate the original gas in place by dividing the hydrocarbon pore volume by the dry formation volume factor, and we get to a number that's around 183 billion cubic feet. And then we multiply this original gas in place by this solution GOR value, and we get to around 12.2 million stock tank barrels. An alternative way of calculating this is to just calculate this, what we call the geologist BOI, or the BOI for gas condensate reservoirs, just dividing BGD, I in this case, so the initial dry formation volume factor, by the solution CGR, and we get a quote-unquote formation volume factor of 8.2 reservoir barrels per stock tank barrels, and we can simply just divide 100 million reservoir barrels by this number, and we yet again get exactly the same answer, which is 12.22 million stock tank barrels. And with that, we are actually 1 minute. We have 1 more minute for questions. Yeah, we have questions here, so I'll just stop sharing. And I don't think we have a. I see there's a lot of questions. Four questions here. So so Mark has a couple of questions. For extrapolation of a black oil table, when an equation of state is available, would you advocate for extrapolating K values to convergence pressure like in the SPE paper, or would you prefer to use a set of reverse differential liberation or CVD experiments instead? Question mark.
Well, it's hard to say. What I think what I said was that there's not a best way necessarily to extrapolate. Usually, you'd like to extrapolate in a way that mimics most closely the process that's giving you those gas oil ratios in between RSI and little RSI. So I don't think there's a right answer. At the end of the day, the way to check is to run a compositional case of the model and the Blackwell case of the model, and see whether the black oil with extrapolation is giving you I think a reasonable match of compositional data performance in the model. There's not really a right and wrong usually for how to do it. I think that's...
No. We need to have a follow-up with you, Mark. Off of the course. That's very good. There's a few other questions here. A good question from that came here is, for instance, when we went into the black oil PVT table that we worked on in the exercise, and even though we are at single phase undersaturated conditions, we have properties provided for oils in the table. So what does these oil properties kind of represent physically?
Undersaturated properties, Well, okay, so yeah, I think I understand. So when you create the Blackwell tables, usually you have an equilibrium vapor on top of equilibrium liquid. They're in equilibrium.
Maybe you can probably draw something, Curtis, if you. I'll make you present it. No. This is a.
Yeah. So I can just add a page here. So yeah, so let's say that you've got this from a depletion experiment or something. You basically got your equilibrium vapor and your equilibrium liquid here together. And so this is at some pressure. Well, what we know is that the dew point of that vapor is equal to the pressure, and the bubble point of that liquid is equal to the pressure. Okay, so this is equilibrium at that pressure. But what you can do then is you can take that gas by itself, okay, away from the oil, same composition here and here. Okay, but now we're gonna be at some new pressure that's greater than the dew point of that gas, right? It could be 50 psi or 5,000 psi, any pressure. And what'll happen is that the volume of that vapor will decrease, you know, compared to what it was at the dew point, because you're compressing it, higher pressure. But if you flash that to the surface, the surface volume of gas and surface volume of oil coming from that equilibrium vapor remains unchanged, right? So when I go to a higher pressure, the only thing that's going to change is, I'm going to redraw this. The only thing that's going to change is this volume. It's smaller because you're at a higher pressure compared to the original volume, right? Same composition, different volume of your gas here, right? So this is the volume of the gas at that dew point, you know, at that pressure. This is the volume at some higher pressure. So what that's going to affect? That's going to affect the BG, right? Because that's the volume of gas. I'm just going to put prime, volume of gas at P prime over the volume of gas from gas. Well, this doesn't change. The denominator, the volume of surface gas from gas, doesn't change. This changes. So the BGD is going to change at this new pressure. Likewise, the gas viscosity at P prime will be larger than the gas viscosity when it's at the dew point, right? So both those two properties will be changing because the density of the gas changes. And you can do the same thing for the oil. You take the oil away, bring it to another P prime greater than its bubble point. And when you change the pressure to a higher pressure, that oil volume will compress and become smaller. It'll affect the BO, not as much as the BG, but okay. It'll affect the BO and it'll affect the oil viscosity. So for the same exact composition, you've got Xi. So the volume of oil of this Xi here that you got at P bubble point is, you know, is going to, is going to be larger than the VO, the exact same composition, but at a higher pressure, P prime. That's going to affect the BO, right, at P prime, even though it's the same composition. Likewise, the oil viscosity will be different here as well. So I think that answers the question.
This BO at P prime,
Yeah,
it's not going to be used because we don't have any oil at P prime, unless we are doing some.
okay, but if you start a water flood,
Yeah, then, so if you do some, then it will
Yeah.
affect at P prime.
yeah, so if you're just in depletion mode
Yeah.
where pressure is decreasing,
Yeah,
you don't need it.
Yes.
But if you do water flooding, then you will need it. Yeah. So if you water flood the fluid initially, yeah, then you'll need it. So, so I think that's
Very good. So I think at this point we'll end this this course, and if there's any follow-up question that you might have, all our emails are available on our webpage. We're typically available for follow-up questions. Again, the material will be sent out, both the recording and all the technical material, the exercise, etc. So if you all have any questions, we're more than happy to follow up on that. And I guess in the meantime, everybody take care, stay healthy, and hopefully we'll see you around for our next course and potential webinars.
yeah, it's been nice. Thanks for getting up early or staying up late.
Cheers.